The theory of conjoint measurement is a general, formal theory of continuous quantity. It was independently discovered by the French economist Gérard Debreu and by the American mathematical psychologist R. Duncan Luce and statistician John Tukey. The theory concerns the situation where at least two natural attributes, or an X, non-interactively relate to a third attribute. It is not required that A, X or P are known to be quantities. Via specific relations between the levels of P, it can be established that P, A and X are continuous quantities. Hence the theory of conjoint measurement can be used to quantify attributes in empirical circumstances where it is not possible to combine the levels of the attributes using a side-by-side operation or concatenation. The quantification of psychological attributes such as attitudes, cognitive abilities and utility is therefore logically plausible. This means that the scientific measurement of psychological attributes is possible. That is, like physical quantities, a magnitude of a psychological quantity may possibly be expressed as the product of a real number and a unit magnitude. Application of the theory of conjoint measurement in psychology, however, has been limited. It has been argued that this is due to the high level of formal mathematics involved and that the theory cannot account for the noisy data typically discovered in psychological research. It has been argued that the Rasch model is a stochastic variant of the theory of conjoint measurement, however, this has been disputed. Order-restricted methods for conducting probabilistic tests of the cancellation axioms of conjoint measurement have been developed in the past decade. The theory of conjoint measurement is related to conjoint analysis, which is a statistical experiments methodology employed in marketing to estimate the parameters of additive utility functions. Different multi-attribute stimuli are presented to respondents, and different methods are used to measure their preferences about the presented stimuli. The coefficients of the utility function are estimated using alternative regression-based tools. Historical overview. In the 1930s, the British Association for the Advancement of Science established the Ferguson Committee to investigate the possibility of psychological attributes being measured scientifically. The British physicist and measurement theorist Norman Robert Campbell was an influential member of the committee. In its final report, Campbell and the committee concluded that because psychological attributes were not capable of sustaining concatenation operations, such attributes could not be continuous quantities. Therefore, they could not be measured scientifically. This had important ramifications for psychology, the most significant of these being the creation in 1946 of the operational theory of measurement by Harvard psychologist Stanley Smith Stevens. Stevens' non-scientific theory of measurement is widely held as definitive in psychology and the behavioral sciences generally. Whilst the German mathematician Otto Holder anticipated features of the theory of conjoint measurement, it was not until the publication of Luce and Tukey's seminal 1964 paper that the theory received its first complete exposition. Luce and Tukey's presentation was algebraic and is therefore considered more general than Debreu's topological work, the latter being a special case of the former. In the first article of the inaugural issue of the Journal of Mathematical Psychology, Luce and Tukey 1964 proved that via the theory of conjoint measurement, attributes not capable of concatenation could be quantified. N.R. Campbell and the Ferguson Committee were thus proven wrong. That a given psychological attribute is a continuous quantity is a logically coherent and empirically testable hypothesis. Appearing in the next issue of the same journal were important papers by Dana Scott, who proposed a hierarchy of cancellation conditions for the indirect testing of the solvability and Archimedean axioms, and David Krantz, who connected the Luce and Tukey work to that of Holder. Work soon focused on extending the theory of conjoint measurement to involve more than just two attributes. Krantz 1968 and Amos Tversky developed what became known as polynomial conjoint measurement, with Krantz 1968 providing a schema with which to construct conjoint measurement structures of three or more attributes. Later, the theory of conjoint measurement received a thorough and highly technical treatment with the publication of the first volume of Foundations of Measurement, which Krantz, Luce, Tversky and philosopher Patrick Suppes co-wrote. Shortly after the publication of Krantz al. Work focused upon developing an error theory for the theory of conjoint measurement. Studies were conducted into the number of conjoint arrays that supported only single cancellation and both single and double cancellation. Later enumeration studies focused on polynomial conjoint measurement. These studies found that it is highly unlikely that the axioms of the theory of conjoint measurement are satisfied at random, provided that more than 3 levels of at least one of the component attributes has been identified. Joel Mitchell later identified that the no-test class of tests of the double cancellation axiom was empty. Any instance of double cancellation is thus either an acceptance or a rejection of the axiom. Mitchell also wrote at this time a non-technical introduction to the theory of conjoint measurement, which also contained a schema for deriving higher-order cancellation conditions based upon Scott's work. Using Mitchell's schema, then Richards discovered that some instances of the triple cancellation axiom are incoherent, as they contradict the single cancellation axiom. Moreover, he identified many instances of the triple cancellation which are trivially true if double cancellation is supported. The axioms of the theory of conjoint measurement are not stochastic, and given the ordinal constraints placed on data by the cancellation axioms, order-restricted inference methodology must be used. George Karabatsis and his associates developed a Bayesian Markov chain Monte Carlo methodology for psychometric applications. Karabatsis and Ulrich 2002 demonstrated how this framework could be extended to polynomial conjoint structures. Karabatsis generalized this work with his multinomial Dirichlet framework, which enabled the probabilistic testing of many non-stochastic theories of mathematical psychology. More recently, Clinton Davis Stober developed a frequentist framework for order-restricted inference that can also be used to test the cancellation axioms. Perhaps the most notable use of the theory of conjoint measurement was in the prospect theory proposed by the Israeli-American psychologists Daniel Kahneman and Amos Tversky. Prospect theory was a theory of decision-making under risk and uncertainty which accounted for choice behavior such as the Allais paradox. David Krantz wrote the formal proof to prospect theory using the theory of conjoint measurement. In 2002, Kahneman received the Nobel Memorial Prize in Economics for prospect theory, measurement and quantification. The classical, standard definition of measurement in physics and metrology. The standard definition of measurement is the estimation of the ratio between a magnitude of a continuous quantity and a unit magnitude of the same kind. For example, the statement, Peter's hallway is 4 meters long, expresses a measurement of an hitherto unknown length magnitude as the ratio of the unit to the length of the hallway. The real number, 4, is a real number in the strict mathematical sense of this term. For some other quantities, it is easier or has been convention to estimate ratios between attribute differences. Consider temperature, for example. In the familiar everyday instances, temperature is measured using instruments calibrated in either the Fahrenheit or Celsius scales. What are really being measured with such instruments are the magnitudes of temperature differences. For example, Anders Celsius defined the unit of the Celsius scale to be 1/100th of the difference in temperature between the freezing and boiling points of water at sea level. A midday temperature measurement of 20 degrees Celsius is simply the ratio of the Celsius unit to the midday temperature. Formally expressed, a scientific measurement is where Q is the magnitude of the quantity, R is a real number and Q is a unit magnitude of the same kind. Extensive and intensive quantity length is a quantity for which natural concatenation operations exist. That is, we can combine in a side-by-side fashion lengths of rigid steel rods, for example, such that the additive relations between lengths is readily observed. If we have 4 1-meter lengths of such rods, we can place them end to end to produce a length of 4 meters. Quantities capable of concatenation are known as extensive quantities and include mass, time, electrical resistance and plane angle. These are known as base quantities in physics and metrology. Temperature is a quantity for which there is an absence of concatenation operations. We cannot pour a volume of water of temperature 40 degrees Celsius into another bucket of water at 20 degrees Celsius and expect to have a volume of water with a temperature of 60 degrees Celsius. Temperature is therefore an intensive quantity. Psychological attributes, like temperature, are considered to be intensive as no way of concatenating such attributes has been found. But this is not to say that such attributes are not quantifiable. The theory of conjoint measurement provides a theoretical means of doing this. Theory considers 2 natural attributes A and X. It is not known that either A or X is a continuous quantity, or that both of them are. Let A, B, and C represent 3 independent, identifiable levels of A, and let X, Y, and Z represent 3 independent, identifiable levels of X. A third attribute, P, consists of the 9 ordered pairs of levels of A and X. That is, the quantification of A, X and P depends upon the behavior of the relation holding upon the levels of P. These relations are presented as axioms in the theory of conjoint measurement. Single cancellation or independence axiom. The single cancellation axiom is as follows. The relation upon P satisfies single cancellation if and only if for all A and B in A, and X in X, greater than is implied for every W in X such that greater than. Similarly, for all X and Y in X and are in A, greater than is implied for every D in A such that greater than. What this means is that if any 2 levels, A, B, are ordered, then this order holds irrespective of each and every level of X. The same holds for any 2 levels, X and Y of X with respect to each and every level of A. Single cancellation is so called because a single common factor of 2 levels of P cancel out to leave the same ordinal relationship holding on the remaining elements. For example, A cancels out of the inequality greater than as it is common to both sides, leaving X greater than Y. Krantz, al. originally called this axiom independence. As the ordinal relation between 2 levels of an attribute is independent of any and all levels of the other attribute. However, given that the term independence causes confusion with statistical concepts of independence, single cancellation is the preferable term. Figure 1 is a graphical representation of one instance of single cancellation. Satisfaction of the single cancellation axiom is necessary, but not sufficient, for the quantification of attributes A and X. It only demonstrates that the levels of A, X and P are ordered. Informally, single cancellation does not sufficiently constrain the order upon the levels of P to quantify A and X. For example, consider the ordered pairs, and, if single cancellation holds then greater than and greater than, hence via transitivity greater than. The relation between these latter 2 ordered pairs, informally a left-leaning diagonal, is determined by the satisfaction of the single cancellation axiom, as are all the left-leaning diagonal relations upon P. Double cancellation axiom. Single cancellation does not determine the order of the right-leaning diagonal relations upon P, even though by transitivity and single cancellation it was established that greater than the relationship between and remains undetermined. It could be that either greater than or greater than, and such ambiguity cannot remain unresolved. The double cancellation axiom concerns a class of such relations upon P in which the common terms of 2 antecedent inequalities cancel out to produce a third inequality. Consider the instance of double cancellation graphically represented by Figure 2. The antecedent inequalities of this particular instance of double cancellation are, and, given that is true if and only if, and is true if and only if, it follows that cancelling the common terms results in. Hence double cancellation can only obtain when A and X are quantities. Double cancellation is satisfied if and only if the consequent inequality does not contradict the antecedent inequalities. For example, if the consequent inequality above was, or alternatively, then double cancellation would be violated and it could not be concluded that A and X are quantities. Discovered that when the levels of A and X approach infinity, then the number of right-leaning diagonal relations is half of the number of total relations upon P. Hence if A and X are quantities, half of the number of relations upon P are due to ordinal relations upon A and X and half are due to additive relations upon A and X. The number of instances of double cancellation is contingent upon the number of levels identified for both A and X. If there are n levels of A and m of X, then the number of instances of double cancellation is n times m. Therefore, if n equals m equals 3, then 3 times 3 equals 6 times 6 equals 36 instances in total of double cancellation. However, all but 6 of these instances are trivially true if single cancellation is true, and if any one of these 6 instances is true, then all of them are true. One such instance is that shown in Figure 2. Calls this a loose, two-key instance of double cancellation. If single cancellation has been tested upon a set of data first and is established, then only the loose, two-key instances of double cancellation need to be tested. For n levels of A and m of X, the number of loose, two-key double cancellation instances is, for example, if n equals m equals 4, then there are 16 such instances. If n equals m equals 5, then there are 100. The greater the number of levels in both A and X, the less probable it is that the cancellation axioms are satisfied at random, and the more stringent test of quantity the application of conjoint measurement becomes. Solvability and Archimedean axioms. The single and double cancellation axioms by themselves are not sufficient to establish continuous quantity. Other conditions must also be introduced to ensure continuity. These are the solvability and Archimedean conditions. Solvability means that for any three elements of A, B, X and Y, the fourth exists such that the equation AX equals BY is solved. Hence the name of the condition. Solvability essentially is the requirement that each level P has an element in A and an element in X. Solvability reveals something about the levels of A and X. They are either dense like the real numbers or equally spaced like the integers. The Archimedean condition is as follows. Let I be a set of consecutive integers, either finite or infinite, positive or negative. The levels of A form a standard sequence if and only if there exists x and y in X where x, y and for all integers I and I plus 1 in I. What this basically means is that if x is greater than y, for example, there are levels of A which can be found which makes two relevant ordered pairs, the levels of P, equal. The Archimedean condition argues that there is no infinitely greatest level of P and so hence there is no greatest level of either A or X. This condition is a definition of continuity given by the ancient Greek mathematician Archimedes, whom wrote that, further, of unequal lines, unequal surfaces, and unequal solids, the greater exceeds the less by such a magnitude as, when added to itself, can be made to exceed any assigned magnitude among those which are comparable with one another. Archimedes recognized that for any two magnitudes of a continuous quantity, one being lesser than the other, the lesser could be multiplied by a whole number such that it equaled the greater magnitude. Euclid stated the Archimedean condition as an axiom in Book V of the Elements, in which Euclid presented his theory of continuous quantity and measurement. As they involve infinitistic concepts, the solvability and Archimedean axioms are not amenable to direct testing in any finite empirical situation. But this does not entail that these axioms cannot be empirically tested at all. Scott's finite set of cancellation conditions can be used to indirectly test these axioms, the extent of such testing being empirically determined. For example, if both A and X possess 3 levels, the highest-order cancellation axiom within Scott's hierarchy that indirectly tests solvability in Archimedean is double cancellation. With 4 levels it is triple cancellation. If such tests are satisfied, the construction of standard sequences in differences upon A and X are possible. Hence these attributes may be dense as per the real numbers or equally spaced as per the integers. In other words, A and X are continuous quantities.